Hello everyone. Next we will start chemistry section for this course, and we will start chemistry by an introduction to atom and periodic properties. Uh, before starting, let's reintroduce what is an atom. Atom in its simplest form is the smallest piece of matter that retains the identity of chemical element. You cannot break it down further and still call it say a goal. uh, and we also know that atom is the basic building block of any matter, and atoms are made up of three fundamental subatomic particles, namely proton, neutrons, and electrons. Protons are the are in the atom's center, called a nucleus. Protons are found in the nucleus of an atom, and there they carry a positive charge. And proton is the sole factor that determines which element you have. If you change the number of protons, you change the element itself. And then we have neutrons. This is also found in the center of an atom, or we can say it is found in the nucleus. And in terms of charge, they are neutral. They do not possess any charge. And for any element, for a element, there could be multiple number of neutrons, and if we have the same element but different number of neutrons, we generally call it isotopes. We will talk about that in next slides in more details. And then we have the third subatomic particle, electrons. These electrons orbit the nucleus in specific regions, and we call these specific regions either cells or energy levels. They have a negative charge, and uh, electrons has a negative charge, and electrons are responsible for all the chemical bondings or the chemical reactions. And we should also note that the number of protons and the number of electrons in an atom is equal, resulting in net zero charge. So basically, atom is neutral neutral and stable, and it is not atom itself is not charged, and the net charge is zero because of the same number of positive and a negative charge. Let's look at the history of atomic structure. Our understanding of the atoms wasn't a sudden discovery. It was a progression of models built on centuries of work. And it started with ancient Greeks. Democritus in around 460 BC proposed the idea of indivisible particles, and he called those particles atom. So he was the one who introduced the term atoms, and he proposed that these atoms are indivisible, meaning it cannot be divided into a smaller part than atoms. And however, uh, the philosophical authorities like Plato and Aristotle argued that matter could be divided endlessly, and they call an atom matter continuously and infinitely divisible. And this concept won for nearly 2000 years, and in the early 1800s, the concept of indivisible particles was revived by the scientist John Dalton, who based his atomic theory on reproducible chemical reactions. And then we have after the discovery of electrons, we got uh, a plum pudding model of an atom proposed by J.J. Thomson. And then uh, Ernest Rutherford introduced introduced the concept of atom with a dense nucleus and electrons orbiting around this dense nucleus. And to overcome the limitation of Ernest Rutherford's model, uh, Niels Niels Bohr proposed a new model with he refined this with a planetary model with a planetary model introducing the idea of this quantized fixed energy uh, level of electrons orbits. And then after Niels Bohr's model, we have this modern atomic theory, which is the most recent and most accurate atomic model. And this modern atomic theory is based on quantum mechanics. Let's look at the Dalton's theory in more details. Dalton theory was the first truly scientific description of the atom, and this model was found on empirical evidence like the law of conservation of mass, and this is based on empirical evidence like conservation of mass. And his main points were that all matter is composed of small indivisible particles called atoms, and we now know atoms are divisible, but the concept of a fundamental particles is still held true. And then he also points that all atoms of a single element are identical. Now we know that there are isotopes with same atomic number but different atomic uh, masses contradicting this point. Then he also mentioned that atoms of different elements have different masses. Different elements have different masses, and chemical compounds are formed when atoms combine in fixed simple whole number ratios. And we can see an example like this. This is water, and you can see there are two hydrogen atoms and one oxygen atom instead of looking something like this. So all the chemical reaction will always have specific integer ratios, not some fraction ratios. And the last point is that atoms are rearranged in chemical reaction. They are never created or destroyed, they are simply rearranged. So when chemical reaction is when chemical reaction takes place, neither atoms are created nor they are destroyed. They are only rearranged in different form. This is where this conservation of mass is related. And it, it, he also mentioned that when the compound decomposes, the atoms are recovered unchanged, because the atoms were neither created nor destroyed. They were simply rearranged in different form. And then in the 1897, J.J. Thomson performed a series of cathode ray experiments that led to the discovery of the first subatomic particle, the electron. So electron was discovered in 1897 in the series of cathode ray experiments performed by J.J. Thomson. In a cathode ray tube, a beam of particles, the cathode ray, we can see here in this blue color, a cathode ray, this cathode ray, this beam of cathode ray is negatively charged. It was known at the time that this cathode ray, the beam of cathode rays were negatively charged. And when he used this negatively charged cathode beam, and he passed this cathode beam through an electric field. Here we can see there's an electric field with a positive and negative charge, and when this negatively charged beam was passed through this electric field, this beam deflected away from the negative charge. We can see in this animation, when the charge is negative in this side, the beam will deflect on the other side, and when the this terminal is negative, the beam will deflect in the other direction. And from the basic principle of charge, we know that the same charges will repel each other, and opposite charges will attract each other. So if you look at the deflection of this beam and the charge applied in this electric field, we can see that the beam is attracted toward the positive charge, or repelled from the negative charge. So he concluded that there should be he concluded that there should be this negative charge which are deflecting this negative beam. And using this interaction between this electric field and magnetic field, using this cathode ray experiment, J.J. Thomson was able to determine the charge to mass ratio of an electron. And as of today, we know that the charge to mass ratio of an electron is 1.75 into 10 to the 11 coulomb per kilogram. And after that, American scientist Millikan found that using his oil droplet test, he found that the charge of an electron is 1.6 into 10 to the minus 19 coulomb. And once we know the charge to mass ratio of an electron and the charge of an electron, using this ratio, we can find the mass of an electron, and the mass of an electron is 9.11 into 10 to the minus 31 kilogram. And after the discovery of this electron, J.J. Thomson proposed a new atomic model, which was later known as a plum and pudding model. he proposed an atomic model with a positively charged sphere with a negatively charged electron embedded inside embedded inside, and this model was later known as plum and pudding model. If we see in the image here, we have this spherical region, and all this spherical region itself is positively charged, and within this spherical region with positively charged particles there were these negatively charged electrons embedded within this sphere, and like this plum on a pudding, and with that analogy it was later known as plum and pudding model. The model tried to account for two properties of the atoms then known. So at that time we knew, the scientists knew that atom there are negatively charged electrons within an atom, and they also knew that atom itself has no net charge. So this model from J.J. Thomson covered those two ideas, or the information known at the time, and then this result of the presence of electrons, negatively charged electrons within an atom, and the fact that atom itself is neutral, meaning there's no net charge in atom itself. He also he proposed that this negative electrons should be embedded within a positive charge, so overall the atom will be net zero charge. However, this model was soon this model was soon disproved by the discovery of a nucleus by Ernest Rutherford in 1907. He was one of the J.J. Thomson's former students, and he conducted his famous gold foil experiment. And this gold foil experiment fundamentally changed the model of the atom. He sought, if we look at the image here, we can see he sought a beam of a heavy positively charged alpha particles. We can see here there's a beam from alpha particle, and a lead screen with a small slit here, and this alpha particle were shot in this gold foil, a very thin gold foil, based on the J.J. Thomson's plum and pudding model. When he performed this experiment, he expected all the alpha particles to pass straight through with minor deflection. So if J.J. Thomson's plum and pudding model was true, meaning all these positive charge were away, like spread within the atom, the positively charged alpha rays should just pass straight through the gold foil with a minimum deflection because of these small charged particles. However, what he saw was that the vast majority of alpha particles did in fact pass straight through the foil. We can see here. So a vast majority of this alpha particle actually pass through the foil without any deflection. And with that, what he concluded was that atom is mostly empty space. If it was not empty, and if it was the same as J.J. Thomson proposed, then all this alpha particle would most of the alpha particle would have been a small deflection. Rather, he saw most of them passed and there were no deflections. So he concluded that the atom is mostly empty space. And the pudding from the J.J. Thomson's model, the pudding of a positive charge could not have been a uniform sphere. And then he also saw that a small fraction out of 1 out of 8,000 of alpha particles were deflected at very large angle. We can see here some of the particles were deflected at a very large angle, and some of them even backtracked to the same position as the source, back to the source. And this back scattering was he concluded that this back scattering was only possible if the alpha particles had struck a tiny extremely dense positively charged center. So tiny extremely dense positively charged core, and this tiny center was later called as nucleus. So based on this very high deflection of some of the particle, he deducted that there should be a small section, a small dense section within an atom where the positively charged particle are concentrated, and and he called this small region as the nucleus of an atom. So based on these findings, Rutherford gave us the nuclear model, and the key features of this Rutherford model are that the atom has a tiny central region called the nucleus, and he also and within this nucleus, virtually all the mass and all the positive charges are located. So the whole mass of the atom is concentrated in the nucleus. And then the negatively charged electrons, he also concluded that the negatively charged electrons revolve around this positively charged nucleus in a circular paths called orbits. And then the model also considers that the atom is held together by the electrostatic force of attraction between the positively charged nucleus and the negatively charged electron. However, there was a massive leap. Even though there was a massive leap in this atomic model, there was a very fatal flaw in Ernest Rutherford's model according to classical physics. So according to classical physics, an electron orbiting nucleus should continuously emit energy and spiral inward. So if this electron was to continuously move, it should ultimately just move inside, spiral inside, and ultimately the atom itself should collapse. However, we know that atoms do exist, So that means there has to be something with the model, and in order to overcome this limitation, Niels Bohr proposed a new theory called Bohr's theory, uh, and this new theory solved the stability problem of Rutherford's model, and the key postulates of this new theory of atomic model is that electrons exist in specific fixed stable orbits, or we can also say discrete energy levels. As long as electron stays in one of these orbits, it does not radiate energy. So we can see here we have this electron is moving in specific energy level. So this is energy level 1, energy level 2, and so on. And if this electron is moving within this same energy level, it will not emit any energy or absorb any energy. However, if this electron was to jump from one level to another level, it will either absorb energy or emit energy. If an electron absorbs a specific amount of energy, and from the chapter light we know the energy is in the form of photons, it jumps to a higher orbit, or we also call it excited state. So if we have an electron here and it gains some energy enough to change its level of energy, it will jump from this level to the next energy level, and uh, it it will observe some energy to do so. And if the electron moving in higher energy level were to emit some energy, it will jump to if or in other words we can say, when an electron in higher energy level jumps to it drops to a lower energy level, a lower orbit, it will emit some energy in the form of photon, and these energy levels are represented by a letter n, and they are sometimes called energy level 1, energy level 2, energy level 3, or they are also called they are also called K, K, L, M, N, and so on. And the energy difference between these orbits, for example, orbit 1, orbit 2, is what determines the energy of a photon emitted or absorbed, and the energy emitted or absorbed is defined by this equation, change in where delta is change in energy. Change in energy is equals to final energy minus initial energy, and this is also given by h times nu, where h is the Planck's constant and nu is the frequency of light. And this model, Bohr's theory, successfully explained the emission spectrum of hydrogen, the spectrum we talk about in the light chapter. Bohr's theory was successful to explain this emission of spectrum of hydrogen. However, this model failed for atoms with more than one electrons, and to overcome these limitations of a Bohr's model, the current and most accurate model of atom was proposed, and this most modern atomic model is called modern atomic theory, and this modern atomic theory is based on quantum mechanical model, or we can also say that this modern atomic theory is also known as quantum mechanical model, and this model was developed in the 1920s by physicists like Schrödinger and Heisenberg. Schrödinger and Heisenberg, and this quantum mechanical model moves beyond the simple planetary view of the Bohr's model, and it uses a probabilistic approach to define the atomic model. And the key principles of quantum mechanical model is the first key principle is the based on Heisenberg uncertainty principle, and it states that it's impossible to simultaneously know the exact position and the momentum of an electron, and this uncertainty principle mentions that since we cannot know the exact momentum, or in other words the velocity of an electron and the position of the electron within the atom, we cannot define the fixed path of electron like it was defined in Bohr's model. So we cannot define a fixed orbit that the electron will take. And the second principle was introduction to orbitals instead of orbits. So instead of fixed path, the Schrödinger proposed an equation that defines atomic orbitals. Now instead of orbits we have orbitals. An orbital is a three-dimensional region of space where there is a high probability, usually 90%, of finding an electron. So orbital is nothing but a region in a space where the probability of finding the electron is around 90, 90%. And we can see in this image here, we can see this within this small section, this the darkness of this fuzzy cloud is the highest, meaning within the probability of electrons being in this section is represented by this darkness of the color. So we can say the around 90% of this electrons of this particular atom will be within this section, and the shape of this orbitals and the energy of these orbitals are not all the same. We can see this orbital will have different shapes and different energy level, based on different energy level, and the shape of these orbitals are generally represented by these letters S, P, D, F, and we can see that these orbitals have different shapes for different energy level. The first orbital, S orbital, is spherical. We can see here small sphere. Spherical p orbital is p orbital looks like a dumbbell like this, or like this, and the d and f orbitals have complex shapes like this. So in conclusion, we can say these orbitals have different shapes based on the energy level. And to identify an element, we already talked about it mostly. Just let's finalize how we defined elements. To identify and categorize atoms, we use two key numbers. First, we have atomic number, and it is represented by capital letter G, and mass number represented by capital letter A. The atomic number is the number of protons, and it is the unique identifier. Atomic number is unique for each element, and it's the fundamental identifier of for an element. For example, every atom with atomic number of 6 is a carbon, so there's no exception. All the elements with the atomic number of 6 will be carbon. And then the other number we use to define atoms is mass number, and the mass number is the total number of particles within the nucleus. And we know the subatomic particles inside the nucleus are protons and neutrons. So the mass number is the sum of all the protons and neutrons within an atom. And this brings us to define isotopes. And isotopes are atoms of same element, meaning they will have same atomic number, but they have a different number of neutrons. So if an atom has the same element number but a different neutron number, that results in different mass number. So we can also say that isotopes have the same atomic number but a different mass number. And whenever we are defining an element, there are two different ways to define an element. Sometimes we will use this expression where x is the name of the symbol used to define an element. For example, if we want to say carbon, we can say carbon is C, and this A is atomic number 6, and G is A is atomic mass, and the atomic mass of carbon is 12, and the atomic number is 6. So when we want to represent carbon, we can either write in this form where we have atomic mass and the symbol used for the element and atomic number, or we can also write it as this form, carbon 12. And if it's an isotope, we can also say here carbon 14, and this 12 is the atomic mass number. And if we were to write this isotope of carbon, then we will have to write it as 14C6. And since the number of proton is equals to the atomic number, and if there's 6, then we know there are instead of 6 neutrons, there are 8 neutrons for carbon with atomic mass of 14. And then we can also define ions. If an atom gains or loses electrons, it becomes an ion. And if electron is gaining if an atom is gaining electrons, it will create a negatively charged anions. If an atom gains charges, there will be net negative charge and we call it anions. And if atom loses an electron, there will be a net positive charge because there are higher number of protons than protons than electrons, resulting in net positive charge, and we call it cations. Now while we use the quantum mechanical model for more accurate representation of these atomic models, Bohr model is still a very useful and a simple way to visualize the arrangement of electrons within an atom, especially for atoms within the first 20 atoms, first 20 elements. And in order to draw this atomic model, sometimes this model is also called not just Bohr model, sometimes it's also called Bohr-Rutherford model. We will start. We have this simple steps to follow. We will start with the nucleus. In the center, we will draw a circle and a small circle in the center, and we will write the number of protons and number of neutrons in the center. And then we will draw the number of cells corresponding to the row of an element for defining this number of electrons. We will use the periodic table and find out how many number of cells or energy level we will have for each element, and then we will fill the electrons for it. We will fill these cells with electrons, and in order to do so, we need to remember that the first cell, r n equals to 1 or sometimes represented by k, can have a maximum of 2 electrons. Second cell can have a maximum of 8 electrons, third can have 18, fourth can have 32, and so on. Here we can see an example of the let's look at an example here. First we have oxygen, and we will start with this inner circle representing the nucleus of an element, and we know the number of protons in oxygen is 8, number of neutron is also 8, and the atomic configuration is 2 and 8. So we start with the inner circle, and then we will draw the next circle representing the energy level of 1, and we know that the first energy level can have maximum of 2 electrons, so we will fill this with 1 electron, 2 electrons. So out of 8 electrons, we have 6 electrons left. Then we will draw the next energy level, and we know that this energy level can have a maximum of 8 electrons. So we will fill the remaining 1, 2, 3, 4, 5 and 6 electrons, and this will represent the electronic configuration of oxygen atom. And the outermost cell of an electron is called a valence cell. And if we look at here, we know that the second cell can have a maximum of 8 electrons, and if we look at the electronic configuration, we only have 1, 2, 3, 4, 5 and 6 electrons. That means in order for this electron to be stable, it can either lose 6 electrons or it can gain 2 electrons. Losing 6 electrons is most unlikely because it requires more energy. So since oxygen has 6 valence electron, it will strongly seek to gain 2 electrons to fill the outer cell. So oxygen will try to add 2 more electrons in order to be stable, or in other words, in order to complete this outer cell. Let's look at an example of calcium. The atomic symbol the symbol used to represent a calcium element is Ca, and the atomic number of calcium is 20. And we will start with inner circle. This will be 20 neon is 10 atomic number is 20, and we can see we will start with the first circle for first energy level, and first energy level can have a maximum of 2 electrons, and now we still have 18 electrons left. So we will draw the second second orbit, and the second orbit can have a maximum of 8 electrons. So we will use 8 electrons here, 4, 5, 6, 7 and 8, and then we will draw this third energy level. And then even though third energy level can have 18 electrons, if we look at here, especially for elements below this 20 atomic number, elements below 20 atomic number, they are generally the third cell is also filled with 8 electrons to be stable. And since we have 8 electrons here, 16, 17, 18, and the total number of electrons is 20, the outermost cell will have 2 electrons. And since the valence cell has 2 electrons, it is easier to lose these 2 electrons to be stable than compared to gaining 6 electrons. And then we also have this neutral gases like neon, represented the symbol is Ne, atomic number is 10, and number of neutron is also 10. Then the first energy level we can have 2 electrons, and second energy level the rest of the electrons are filled here. And if you see here, the maximum number of electrons in the second orbit can be 8, and if you count these electrons here, we have 8 electrons, and we can say it's completely filled, meaning this kind of this kind of element with completely filled valence shell are chemically inert, and we generally call them inert gases or noble gases. Then let's formalize the concept of a quantum mechanical model, uh, which is necessary because the Bohr's atomic model is only was only able to define the behavior of hydrogen, and it fails for anything complex than hydrogen atom. And as we said, quantum model is based on a probability, and the first probability, and the quantum mechanical model is all. We can also say that the quantum mechanical model is based on uh, based on wave and particle like nature of electron movements. So the first we have Heisenberg's uncertainty principle, and it says the act of measuring an electron's position changes its momentum. And when we are talking about momentum, we are basically talking about the velocity of the electron, and we cannot know both the position and the velocity of an electron, and it's defined by Heisenberg's uncertainty principle. And then we also have Schrodinger's equation, and the equation proposed by Schrodinger is the gives when we solve the Schrodinger equations, it will give us the wave function represented by this symbol psi, and this wave function defines the energy and shape of atomic orbitals. And atomic orbitals are defined paths, but these orbitals are not defined paths, rather orbitals are a region where where we have a 90% chance 90% probability of finding an electron, and we should be careful that this quantum mechanical model is based on orbitals rather than orbits from Bohr's model. And if we were to solve Schrodinger's equation, naturally we will get a set of numbers as a result, and these numbers from the solution of the Schrodinger's equation is like the address of electrons. So we can say these numbers are basically address of an electron, meaning if we know all the numbers obtained from the Schrodinger's equation, solution of Schrodinger's equation, we can accurately define where the electron is at particular time. And the solutions to Schrodinger's equations are called quantum numbers, and there are four different quantum numbers, but three of the four quantum number define the orbital itself. And the first quantum number represented by n, or the energy level, is the principal quantum number. And principal quantum number is basically the energy level or the cell represented by n, and it's given is written as 1 2 3 and so on. Sometimes you will also see lmn o and so on. So the higher the number, the higher the number means higher energy level. So we can say higher number equals to higher energy level. And then we have angular momentum, and this is generally represented by letter L. And this quantum number describes the shape of the orbital. So this quantum number will define the shape of the orbital and is generally represented by these letters S, P, D and F. And these numbers vary from like this. So 0 is S, 1 is P, 2 is D, 3 is F and so on, and it can go up to n minus 1, where n is the energy level. So basically for first energy level, this will be n minus 1 is 0, so we will only have s orbital. For second second energy level, this is 2 minus 1 is 1, so we will have s and p orbitals. And then we also have a magnetic quantum number represented by ml. Sorry, this will be l, not 1. ml, and this defines the specific orientation of the orbital in 3D space. For example, the p subshell from here, this p subshell can have three possible orientation. Sometimes you will see it written as -1 0 1, or sometimes you will also see px py pz. So basically principal quantum number describes the energy level. Orbital angular quantum number, or sometimes also called azimuthal quantum number, defines the shape of the orbitals, and magnetic quantum number gives us the orientation of the orbitals. And we can see all this possible number of each quantum number. For energy level 1, the possible angular momentum is 0, and the cell symbol is written as K. Subshell we only have S subshell given by this equation, and then number of orbital is calculated using this equation. This is sum of 2 times L is orbital angular quantum number plus 1. So if we were to calculate the number of orbitals for energy level of 1, this will be 2 times L is 0 plus 1, so this is 1, and so on. We can calculate for all this. So number of orbitals for one energy level of level 1 is 1, energy level 2 is 4. If we look at here, we can have S and P. and this S subshell can have only one orientation, and this P subshell can have three orientations, px, py, and pz. And if we add one orientation from S subshell and three orientation from P subshell, we can have a total number of uh, four different orbitals. Similarly, if we look at the energy level 3, we have S, P, and D subshell. S subshell can have one orientation, P subshell can have three orientations, and D subshell can have three orientation, resulting in total 9 orientation, and so on. And the number of electrons within one specific energy level is given by this equation, where n is the energy level. The first energy level can have 2 electrons, second energy level can have 18 electrons, third energy level can have a maximum of 18 electrons, and fourth energy level can have maximum of 32 electrons. And in order to draw the electron configuration based on the quantum mechanical model, we will follow three fundamental rules, often called the filling rules, and this is also called filling rules. And this will give us this exact location of electrons, and this exact location is defined by four quantum numbers. And the first fundamental rules we need to follow to draw the electron configuration for using quantum mechanical model is Aufbau principle, also called building up principle. This is the energy rule, and basically what it says is that electrons are lazy, and they will always occupy the orbital with the lowest available energy first before moving to higher energy level. And then we have, let's look at an example. Electrons always fill the 1s orbital completely before moving to 2s, and 2s before moving to 2p, and so on. First it will completely fill this and then move to other energy level, other orbitals. And then we have a Pauli exclusion principle. This principle limits the number of electrons in any one orbital. It states that no two electrons in the same atom can have the same 4 quantum number. Meaning no electron will overlap to each other. All since the quantum number, 4 quantum numbers are like the address. If two electrons have the same address, that means they are overlapping with each other, which is not possible. So Pauli exclusion principle states that no two electrons of the same atom can have exact same set of all 4 quantum numbers. And we should also mention that that a single orbital can have only maximum of 2 electrons. Orbital can have a maximum of 2 electrons, and even if all the 3 quantum numbers are same, one the two electrons within the same orbital will spin in two opposite direction. One will spin up, one will spin down, resulting in different quantum numbers. And then we have Horn's rule. uh, when you have orbitals of the same energy, like the 3p orbitals, electron will enter them singly, especially for 3p or 5d orbitals. Instead of filling two electrons within an orbit, they will spread out and enter them singly with parallel spins. Finally, let's visualize the outcome of quantum mechanical models. We can see here in the first diagram, this shape of this orbital is defined by this wave function, which is the solution of Schrodinger's equation. And we should also note that this wave function is what defines the boundary of this orbit, the shape of the orbits. First, we have S sub cell. We can say that this is the S sub cell is a spherical body, spherical orbit. And then we have P sub cell. Within P sub cells there can be three orbitals. We have px orbital, py orbital, and pg orbital. And we can see the shape of this orbital looks like a dumbbell shape, but for px it's oriented in x direction, py it's oriented in other direction, in y direction, and pg it's oriented in g direction. Similarly, for d sub cell, we can see there are 5 different orbitals, and the shape of these orbitals are complex. And if we move further, for example, to f sub cell, f orbitals, we will have even more complex shapes. We will talk about how to draw the electron configurations, how to calculate the electron configuration in next video.